Hey, math people, we're looking at lecture 9, the last one of this run through all the differentiation rules in Calc 1 differential calculus. So we're going to start by building intuition for what's called the inverse derivative. Fun. We'll look at a few of those examples, then we'll derive the derivative of arcsine, and then go through those rules, and then do some derivative things with that. Remember, this video is for you, Josh. So the point being is to use pause, use the timestamps, use this in a way that is efficient for you. All right, let's do this. Let's math. All right, so we're starting with like a warm-uppy thing here. So if I'm looking at x squared plus 1, find the derivative. All right. And then with that derivative, I fill out the table over here. So yeah, find the point the point where the function exists for 0 through 4, and then same thing for finding the slope 0 through 4. Okay, the point is we're going to come up with a pattern. You're like, why are you asking me to do this, man? I'm clicking this because I want you to teach me inverse derivatives. Okay, look, there's a point here. So if you do that, and then if you find the inverse function, if you remember how to do that, you flip-flop. You would replace this f of x with a y, flip x and y, and then solve for the new y. So you would find the inverse function of this. Find the derivative g prime. What we should notice is a pattern. That is all I'm going to be demonstrating right now. So if you want to wait for me to tell you what that pattern is, feel free, but alternatively, you're taking the derivative, you're plugging in 0 through 4 for the original function and derivative, find the inverse function, then find the inverse function's derivative, and you should see a pattern when you plug in these values. All right, here's how it goes. So if I were to find f prime, it's just 2x. So when I plug in 0 through 4, I get these values, which, look at that. And if I were to plug in the derivatives, I would get 0, 2, 4, 6, 8, and that should make sense because the derivative is just 2x, just even numbers. Now, if I were to go out of my way to find the inverse function to this x squared plus 1, I would end up getting the square root of x minus 1. Okay, and the way we did that is through replacing x with y, solving for the new y. Technically, there's a plus or minus here, but I'm just fixing x to be greater than 0. And then I found g prime by chain rule. I took the 1/2 brought up front, subtract the 1 here, kept the inner the same, and then derivative of inner is just 1. So it's this expression. Now, when I plug in the output at each of these moments, into the derivative, you'll notice some pattern. You'll notice that, okay, well, 0 turns into like an undefined value, 1 over 0. 2 turns into 1/2. 4 turns into 1/4. 6 turns into 1/6. 8 turns into 1/8. So this is the whole point of inverse derivatives, is that if I have an inverse function, what I can do is if I'm taking the derivative of that, it's just going to be 1 over whatever the original function's derivative is at that output, which sucks that that's what it sounds like in wordy language, because you're probably thinking, what? Because that's what I think when I say that too. But the takeaway is, if you flip-flop the input and the output, which is what inverse functions do, then the slope would be the reciprocal. That's the most word efficient way. And even then, there's some hand waviness within that. Let's look at the pattern in action. Okay, this is the actual derivative. What I like to do is, if you have f prime is q over p, then the derivative of the inverse at y is p over q. So you can write it this way as well. They both mean the same thing. The idea is two-stepped, multifaceted. Your input changes from, instead of x, it's y. And then if you're taking the derivative of that inverse function, it's going to then have a reciprocal slope. That's the idea. It's a little like, okay, and so that's why I don't think it requires like a full day of teaching this. It's so minor. It's like one question on the AP exam. All right, so if I have x cubed and I'm looking for the inverse derivative at 8, we can do it in 2 ways. See if you know the 2 ways. 3, 2, 1. First way, just find the inverse derivative, which is cubic root of x, and then plug in that 8. You get 1 over 12. The alternative is to, here it is, find the derivative f prime of the x cube, and then you get 3x squared, and you think, what would I have to plug in? Because, well, 8 is the output. You're not plugging in 8 into this inverse idea, which is taking the reciprocal. You're finding what the input would have been in order to get an output of 8 for the original function. And that's 2. Because if you plug in 2 here, 2 to the third power is 8. So you're plugging in 2 into this derivative. So that was the first step. And you get 12. And the second step's a nice and easy one. You take the reciprocal of 12, which is 1/12. This is the new rule. This is kind of like old algebra plus just derivative stuff. Yeah, how do you feel about that? Let's give it another go. We're going to give 2 a shot. Yeah, so we're given a function. You're given that g is the inverse of that. You're given that f of 2 is 9 just because they don't want you to solve it out. They want to make you do that. Find g prime of 9. So let's use the new rule. What we want to do is utilize the 2 and the 9. Okay, if I'm finding g prime of 9, what is the input for f when our output is 9? Okay, and I'm going to be plugging that in to the derivative of the original function first, and then I'll take the reciprocal of that. So in practice, you're taking the derivative of this expression, and you're going to plug in a number. I wonder what that number is. Then take the reciprocal. Give it a go. 3, 2, 1. Took the derivative. I plugged in the number 2. I didn't plug in 9. I plugged in 2 because that's the input at that moment. So I get 12 again, and then I flip it, reciprocal, to get 1/12. So it's 2 steps, or 2 like big ideas. Is that you're taking the derivative at the input for whatever the inverse's derivative's input is, and then you're going to take the reciprocal of that. That's the second step. Give it a go again. Here, I don't even give you a function. So this is just strictly practice with that idea. Do I want to give you a hint? Hint in 3, 2, 1. So hint is, okay, I'm finding the inverse's derivative at 4. Okay, so I wonder what that input would be. And then I'm taking the reciprocal of that input. 3, 2, 1. It's just 1/5. Oh man, I love this new rule. I get to save so much time with it. Yeah, so here's the thing, is that I'm finding g prime. G is the inverse of f at 4. So the input when you have an output of 4 is 3. So I'm taking the derivative of the OG, the original f, at 3, and I'm getting 5. And then I'm taking the reciprocal of that to get 1/5. That's the rule, people. One last time. Give it a go with sine. And this is a good segue into inverse trig derivatives. 3, 2, 1. All right, so yeah, if we know the derivative of f of x is cosine x, derivative of sine is cosine, and I'm finding g prime of root 3/2. So I'm thinking, okay, well, wait, unit circle. For sine, root 3/2 happens at pi over 3. I just give you that, by the way. So, all right, I'm plugging in pi over 3 into the original function's derivative, which is 1/2. Take the reciprocal of 1/2, you get 2. I'm going to verify this, so I'm setting up for something here. I'm going to verify this with inverse trig derivatives, which are coming right now. So that concludes inverse derivatives. Segueing over to inverse trig derivatives. I'm kind of 2 bird 1 stoning here because these are kind of like the little bonusy kind of last topics of differential calculus. We don't really use these 2 sections that much. Anyway, I'm going to derive the derivative of arcsine real fast. So I'm going to use implicit differentiation. Get ready for it. 3, 2, 1. Taking the derivative of both sides after I apply sine to both sides, because I don't know this derivative yet. I do know the derivative of sine. So I take sine of both sides to cancel with the arcsine on the right side. I take the derivative with respect to x. I have a function within a function here. Yeah, so I take derivative of outer, which is cosine, keep inner the same, and then derivative of inner, that's implicit differentiation. Let's go. We're dancing with derivatives. We get dy dx there. Derivative of x is just 1. We divide out that cosine, so we get 1 over cosine y. We generally don't write derivatives with respect to its dependent variable. I have cosine y. I want to write it as sine y. There it is. I want to write it as sine y. And the reason why is because I know sine y is equal to x. I want to write this as an expression of x. So since I know that relationship, I want to rewrite cosine y as sine y. And the relationship that I know that connects cosine of a thing and sine of a thing is the Pythagorean identity. There it is. So then I went ahead and I scooted over that sine squared. I took the square root. I just took the positive piece because we're just kind of dealing with a positive scenario here. And then I said, okay, this is going to be the square root of 1 minus sine square y. I know that this sine y is just this x. So voila, there's the derivative of arcsine. It's 1 over the square root of 1 minus x squared, which kind of sucks. And that is the derivative. All right, there's 5 more. Do you want to do all 5 more by hand, slowly, like this? No? Me neither. So here are all 6 inverse trig derivatives. Bam. Bam. Yeah, let's look at the patterns. Okay, arcsine and arccosine, they look like they're the same, but it's just, arccosine is just the negative, so the co-function of sine, cosine, is just the negative version of that. Arcsecant is this monstrosity, good luck with that, and arccosecant is just a negative chilling up front. Arctangent, this one's actually useful, 1 over 1 plus x squared. So the arc cotangent derivative is the negative version of that. The co-functions are just negative. So you really only have to know the first, these 3, and then, you know, the other 3 is just the negative versions of those. So we do use arcsine occasionally, the derivative of arcsine. We also use this quite a bit, actually. The derivative of arctangent being this expression. This is actually oddly enough useful in later calc, and you're probably wondering why. And I'll get to that in when we do integrals. All right, so I want to verify a thing here. So if you have arcsine, compute, compute when we're finding the derivative at root 3 over 2. So use your new definition. So what you're doing, so yeah, there's two parts to this. Take the derivative using the new definition, plug in root 3 over 2, and then find when its slope is equal to 1. So whatever that means, right? 3, 2, 1. Here's the thing, this is a match from the problem we did before I did the derivation of arcsine. What I did was I wrote the derivative of arcsine, it's this expression, and then I plugged in root 3 over 2. If you plug that in, you get 1/4 in this radical down below, which is just 1/2. And then the reciprocal 1 over 2 is 2, which is a match with this 2 right here. So, you know, the idea of inverse derivatives works with the idea of derivatives of inverse trig functions, which should make sense. All right, and then if I want to figure out when the slope of this thing arcsine is equal to exactly 1, I'm setting this expression equal to 1. I suppose that happens at 0. And I can go ahead and verify that by graphing what arcsine of x looks like. And if you don't know what arcsine of x looks like, you're pretty normal. Yeah, so that should make sense. If I were to graph the tangent line at that moment, that appears to be the same. So when x is equal to 0. Right, local linearity. This is arcsine, by the way. Arctangent looks like this. That's the only other one that I think is kind of useful. Arctan goes forever. Oh, and here's a fun way connecting arcsine and arccosine and why they're just negative versions of one another. Take a look at this. Arccosine of x. You know, just consider any moment. Consider when, you know, x is equal to 0, for example. Right? The slope here versus the slope here. It's just the negative version of it. This is just a negative 1 slope. This is just a positive 1 slope. So kind of cool how they connect. All right, fix the inferior notation of the inverse tangent and then compute. I don't like this notation. I don't like this. Writing like tangent to the negative first x, in my opinion, just gross. You saw me the way I typed it here. I typed it as arc. So sine raised to the negative first, which, that's not what that is, actually. These are the same thing. So the reason why I don't like this notation is that, generally speaking, if I were to graph like sine squared x and sine of x all squared, this would be a very small rant, I swear. I'm almost done with it. These are the same. Okay? These two are the same. These are the same. These are the same. But if I do that with sine, inverse sine, so this is arcsine, right? I'll get rid of these. This is arcsine. Clearly, these all graph on the same exact curve, right? So then technically, shouldn't this be sine of x all raised to the negative first, right? Based on that logic. Nope. Oh, that? Oh, this? Oh, blue here? Nah, man, that's cosecant, man. What? And that's by notation. This confusion is by notation. So yeah, this means take the reciprocal, right? So these two are the same, but alas, these two are not. And that's an oops. We messed up, guys. That's a sorry. So anyway, write this as arctangent and then take the second derivative. That's fun. 3, 2, 1. Yeah, so whoever made that notation, you messed up math for a long time there, buddy. So the derivative of arctan is this expression. So then the second derivative is just the derivative of the derivative. And hey, that's just a quotient rule. So I ran through quotient and I got negative 2x over the 1 plus x squared. More practice. See if you can practice it with chain, with product, with quotient. Give it a go. 3, 2, 1. So within the first one, I saw a function and a function. So that is chain rule. So I left that x squared inside of the derivative, and then I multiplied by the derivative of that to get 2x. Simplified it out. You get this expression. Product rule. So I did keep first, derivative of second, plus derivative of first, keep second. And you can't simplify that. That's too much of a mess. The last one was a quotient, so I did quotient rule. So I did keep first, so low d high, low, and then d high minus high, d low, and then all over low squared. And I did just clean it up because I had a fraction inside of a fraction, so I just multiplied in 1 plus x squared into both the top and the bottom and cleaned it up just a little bit. Moving on to the next one. Okay, so next is tangent line at 2 for arc cosecant. So do the normal derivative stuff, take the derivative, plug in 2 into the original function, you get that output, and use point slope. 3, 2, 1. All right, here's point slope. If you were to plug in 2 into the OG, the original function, you get pi over 6 using trigonometry. So go back on your trig if you can't see that. I can explain this part. Arccosecant is the same as arcsine of just the reciprocal on the inside. So arcsine of 1/2 is pi over 6. All right, take the derivative of arccosecant. You get this expression. Plug in your 2, and that's the slope. So plug in your slope for m, plug in your pi over 6 for y1, and you're already given the x1. That's it for you. I just want to graph it because why not? We can learn off of it. So if I graph arc cosecant of x, that is a fun looking function. It looks like that. And if I want to find the 0.2 comma, well, whatever the output is, pi over 6, here it is. So I'm just finding the slope at this moment. Not too bad. Y is equal to, here's the slope at that moment, 2 square root 3. And then just plug it into point slope. X minus 2, and then plus that pi over 6. Oh. So to end the day here, people, I made a small oops, and it's a good learning moment. So find the error. This was all scripted. I made an error here. It's an easy mistake to find, truly. What is the derivative? So I'm going to hint at it right now. What is the derivative of our cosecant? It isn't this expression, it's the negative of this expression, right? It's a cosecant. So this should just be negative. And that's a very easy fix right there. Bam, there's that tangent line. All right, that's it. Negative right here. Math on. That was on purpose.